So let's talk about what this course is about. To put it in really simple terms, we have two parties, which for the moment we'll just call them Party 1 and Party 2. Party 1 and Party 2 want to have some sort of communication, and so in particular Party 1 has some message M, and Party 1 would like to transmit message M over to Party 2, because that's how communication works. So at the end of this flow of communications from Party 1 to Party 2, now both parties share this message M. Well, so calling them parties is sort of boring. In cryptography, we have sort of taken as commonplace to refer to these two communicating parties as Alice and Bob, which I'm sure that some of you will have heard used before. Alice and Bob having a conversation. But really, Alice and Bob, these are just ways to anthropomorphize, to use a big word. Two parties are having a conversation. They certainly don't have to be people, right? I mean, Alice might actually be a web browser, and Bob then being a corresponding web server. Alice might be the operating system of your computer. And Bob might be the disk. So, sort of obvious when you have like a web browser that wants to have a communication session with a web server, you can sort of visualize, that sort of thing, because it happens all the time, right? We use web browsers to make connections to websites, and then those two things exchange information. That's communication, right? If you have, your operating system, if you're using an operating system that's encrypting data to protect it before it's written to disk, well, that's this example. Other examples might be that Alice is maybe an ATM machine, and Bob is a central bank. Right? So in this case, you walk up, there actually might be human parties involved. Maybe Alice walks up to an ATM, and the message that Alice is sending, well, Alice isn't really sending any message at all. The ATM is sending messages, but the messages from the ATM on Alice's behalf are things like her PIN number, or the amount of money that she wants to take out, or things like that. So Alice and Bob are the way that we think about these two communicating parties, but you should always keep in mind that Alice and Bob are really just stand-ins for really just a huge number of potential settings in which you have these two parties that want to communicate. Okay, well, so fine. This all works well and good. We can do this, no problem. But we're not really doing crypto here, right? All we're doing here is communicating a message from one party to another. What makes cryptography, in the words of Ron Rivest, who, if you've heard of the RSA algorithm, he's the R of RSA. Ron Rivest says that cryptography is communications in the presence of an adversary. So I'll write the adversary in red because we think of red as being bad somehow. So Alice wants to send this message M to Bob, and there's this adversary. Now, of course, the adversary, if it's just sort of looking at the wire, well, Alice has the message M. She sends it to Bob, so Bob now has the message M. But of course, now the adversary has message M too. So this brings us to some points already. So there are different types of adversaries. And we're going to be pretty informal at first. So I'll become much more formal as we move along in the course. But the first type I want to consider is what I'll call a passive adversary. So a passive adversary simply observes what's on the wire. Passive adversary observed only. More generally, we can consider what are called active adversaries. And active adversaries really sort of capture, reality of real threats. So rather than just having a wire that's being observed by the adversary, there isn't actually a wire there at all. What's here is a network, some sort of communication network. And an active adversary, we actually imagine, controls the network. So active adversaries can modify, drop, add, make up traffic on the wire. So passive adversaries and active adversaries obviously are very different classes, different powers, right? The adversary in the passive case simply observes stuff on the wire and tries to achieve something. Maybe it's learning what the message M is. Active adversaries, of course, can observe, but they can also modify stuff, add stuff, drop stuff, make it up. So maybe what Alice sends is M, and the adversary, who is controlling the network, puts a message M prime in its place, and now what Bob has is a message M prime. So this already brings us, it should be pretty clear that there are two different things going on here. Right? The first one is that we want to be able to send M. Alice wants to be able to send M to Bob. And you probably already have in mind some first sort of cryptographic goal that in some way the adversary shouldn't be learning what M is. And we've just identified the second cryptographic goal, which is that if Alice sends M, then Bob should receive M and not M prime. So this already brings us to, I'll write this in a different color. This brings us to what I'll call the fundamental challenges, the fundamental maybe security goals, the fundamental goals, yeah, that's better, of cryptography. The fundamental goals of cryptography. Number one, this is the one that everybody thinks of when I ask them what cryptography is used for. First one is privacy. Right? This is the one that people think of immediately. They think, well, okay, if Alice sends M, she wants for Bob to receive M and, or not receive, but at least be able to learn by some kind of processing M. And anybody else who is not Bob should not learn what M is. So privacy, I think this is like of the message. The second goal, which the current picture is showing, is authenticity. So by authenticity, what do we mean? By authenticity, we mean that what is received is what was sent. These are the two fundamental goals of cryptography. We're going to spend essentially the entire course, and this is a 10-week course. We're going to spend really probably all told like 9 of the 10 weeks of the course trying to figure out how we achieve these two fundamental goals in a variety of settings. So in particular, if you take a fundamental goal and you take a type of adversary, so goal cross adversary model, adversary type. We'll hear various adversary model, attack model, adversary type, those kinds of things. If you take a goal, an adversarial model, what you get from these two is what we'll be calling throughout the course a security notion. So an example of a security notion might be I want privacy against passive adversaries, which is different. It's a different security notion than privacy against active adversaries, and it's a different security notion than authenticity against, say, passive adversaries. Okay, so again, we're being very informal, even though we've got symbols already on the screen. This is all still very informal because a big part of what this course is going to be about is defining what it is that these things, these terms actually mean. So, what does privacy mean? And I don't mean in some, we could sit around in the class. In fact, if we were in the class together, I would, at this point, start asking you, what does privacy mean? Like, give me some, let's try to, establish what it means for a message to be private. For us, for modern cryptography, is not going to be some fuzzy English language, notion. This is actually going to be some formal mathematical idea, right? We're going to take this really fuzzy term, privacy, and we're going to boil it down to a formal mathematical description that is in terms of the adversary and its powers and the information that it gets access to, and what kind of privacy providing mechanisms Alice and Bob are using. All of this we're going to distill down to a formal definition of what privacy means. Likewise for authenticity. But for now, let's stay at sort of this high level. So as I said, this is the majority of the course, is figuring out how to achieve these two fundamental goals of cryptography in the presence of adversaries. Right. Let's talk a bit about how Alice and Bob might achieve, and let's stick with the privacy goal for a second. So let's I guess I don't need to change anything on the picture. Well, so clearly, if Alice just sends M on the wire and Bob, assuming that the adversary is passive, maybe it's active, it doesn't do anything, but if the adversary's goal is to violate privacy somehow, then what we informally expect to be the adversary's goal, right? I'm using this word a lot because I'm lacking imagination at the moment. But so Alice wants to send M, she wants Bob to receive M, and she wants the adversary not to receive M. Well, if the adversary is even just passive and can observe what's on the wire, the adversary in this picture is going to learn M. So this is clearly not going to do for Alice and Bob. So what we think of then is Alice is going to perform some kind of processing, and we'll call this processing E. So maybe this is some sort of algorithm and more particularly, it's supposed to be some kind of privacy providing algorithm. Well, then what? That means then that let's just say that the adversary is passive. So here is, make a bit of space here. What arrives at Bob's communications port is this script E, calligraphic E of M, and of course the goal is that Bob should be able to learn what M is. So we're going to need that Bob can undo this thing. So not only do we need to be privacy providing, but we need Bob to be able to undo. So Bob computes or undoes. Maybe undoes is good for the moment. So Bob undoes E to learn. Well, fine, that's all well and good. So we've got some privacy providing algorithm that Alice is running that is supposed to be somehow hiding M from the adversary. And since she wants Bob to be able to learn what M is, Bob needs to know how to undo what E does. So this privacy providing algorithm also needs to be, in some sense, invertible. I don't necessarily mean this in the mathematical sense, that there's some proper inverse algorithm. But whatever this algorithm E does, it needs to be invertible by Bob. Well, okay, then what is E doing that's going to prevent A from also being able to undo what E does to learn M? Well, this brings us to probably the most fundamental assumption that we'll make in the class, and we'll say it once, and then it'll just be out there for really the rest of the course. And I apologize if this is a bit sloppy. This is my first time trying to use one of these writing tablets, and it actually takes some getting used to try to write on the tablet when you're actually looking at the screen instead of looking at where your hand's writing. In any case, the fundamental assumption that we're going to make in this class is that all of the algorithms are public knowledge. So the full algorithm, the full description, the code, everything, the whole algorithm for anything that we do in this class, the algorithm itself is publicly known. So, if I tell you, here's the algorithm that's going to process M and provide privacy for the message. If I tell you what that algorithm, if I tell you there is such an algorithm, then I'm going to assume that you actually even know what the algorithm is. So, for example, if you want, you can run that algorithm yourself locally. Everybody can do this. This assumption, it's one that we use because, for two reasons. One is that in many cases, that is the fact. So if you're running one of the algorithms that's been standardized by NIST, for example, or appears in an RFC or something like that, then it's clear anybody can go and look at that standard or that RFC and implement the algorithm and run it themselves locally. The other is that we've learned time and time again that it really makes no sense to try to keep the algorithm itself secret. This has always turned out to be a bad idea. Companies have learned this repeatedly, that they'll embed some kind of processing in a DVD player or whatever, a television set, some sort of DRM protection, whatever. They'll embed some kind of processing that's supposed to provide privacy, say, to the content, and think that this is going to protect them. And some disgruntled employee slips an envelope under the door of somebody as they're fired that describes the algorithm, or some kid with a lot of time on their hands reverse engineers what the algorithm is. And that means that as soon as the algorithm is out, then if you're somebody like a DVD maker, you've now shipped a crap ton of DVD players that have this algorithm in it, and now they're all broken. And you have to either recall them all and do it all over again, or you have to live with the fact that you now have no protection at all. So this is a bad model, and so we're not going to use it. The fundamental assumption that we're going to make in this class, and that's made throughout modern cryptography, is that all algorithms are known. That said, we have to come up with some way to create some sort of asymmetry between what Alice can do and what Bob can do, and what the adversary can do. Because if the adversary can do everything that Alice and Bob can, then, well, the adversary really is just like an honest party in this communication. So we have to come up with some way to create some asymmetry between the honest parties and the adversary, the dishonest party. So what we do in practice, and of course you probably already have this in mind before I even write it, is that, yeah, there's going to be some privacy providing algorithm here, but since that's public, make myself some room, whoops, and I'm going to do it in blue. Since this privacy providing algorithm, the algorithm itself is known to be public, what we're going to do is equip it or add to its inputs this value k, which you probably are already guessing where I'm going with this. This k is the key. Call this the key. And this is secret. So Alice knows the key. Likewise, Bob knows the key. And so it's not just that we want for this privacy providing algorithm to be invertible, but we want it to be invertible. Maybe I'll change back. It's not just invertible, because if it was just invertible, then anybody could do it. We want it to be invertible by holders of the key. Yeah, only the people who hold the key should be able to invert or undo what he does. So now we can make this a little bit more formal over here. So Alice, on her end, has computed this E sub k of m to create some new object to put on the wire, and it goes through the network. And Bob, who's also in possession of k, and of course knows what the algorithm is, because everybody knows that, Bob computes effectively the inverse of ek on ek of m. And by virtue of computing the inverse of ek on this thing, he learns m. Yeah? And the adversary, who is not in possession, is not a holder of the key, we want it to be the case that the adversary doesn't learn m. Yeah? That it's only invertible by holders of the key. Now, what we'll have to settle for in practice is that it's only invertible, it may be invertible by people who don't hold the key, but only if they're willing to compute for an extremely long time, do lots and lots of computational work. This is going to be one of the central ideas of the notions we'll develop, is that when we're talking about privacy, say, versus an active adversary, we're really going to make claims like no efficient algorithm, no efficient adversary A can, for example, compute the inverse of E sub k on the ciphertext, this object here, E sub k of m. So let me add this then to our fundamental assumption, because this really is the punchline of this fundamental assumption. All the algorithms are public, only the key is secret. What is this privacy providing algorithm called? This is, everybody knows this. Everybody who's ever watched a James Bond movie knows what this thing is called, right? This privacy providing algorithm is called encryption. So let's maybe we can erase this. This isn't just a privacy providing algorithm anymore. Let's give this thing a proper name. This thing is an encryption. Encryption algorithm. And the encryption algorithm takes a secret key and a message, and it outputs some string, some object on the wire, This whole thing here is called the ciphertext. So produces, we call it ciphertext. Yeah. So it's a ciphertext that appears on the wire. And Bob needs to compute, I've been calling this thing the inverse of E sub k, the inverse of the encryption algorithm on M. This is the ciphertext. So, but the inverse, what do we really mean when we say the inverse of E sub k? Really what we're talking about is the decryption. So what Bob computes is not the inverse. So what Bob computes is the decryption. Decrypts E sub k of M. Learns M. Good. Okay. Well, so we've addressed the idea of privacy, loosely speaking. Yeah. We're going to spend probably a week, maybe not quite a week, but certainly all of one lecture and part of another, trying to sort out exactly what privacy means in this setting. This setting, by the way, I said it a moment ago, but I didn't write it down, so I probably should. This setting where both Alice and Bob share a key K, this is actually called the symmetric setting. So this is a symmetric. Actually, let me zoom in a bit, that might help. This is a symmetric key encryption algorithm. So what do I mean by symmetric key? Meaning that the two parties who are communicating share a key. So they're symmetric with respect to the key. The adversary who doesn't have the key, this is how we have created an asymmetry between what Alice and Bob can do and what the adversary can do, because the adversary doesn't have the key. And so even if the adversary has a lot more computing power than Alice and Bob, which we typically assume is the case, for example, Alice might be a web browser and Bob might be a web server, and maybe their communication only lasts for a minute or two, while Alice downloads the web page and then uses it and clicks off to another site. Maybe the particular communication that Alice and Bob have with respect to that one web page is very short-lived, but the adversary can collect the traffic that's on the wire and then sit offline and do lots and lots of work. If Alice is using her bank's web server to check on her balance, there's all sorts of stuff that gets transmitted that Alice might want to be private. For example, her password or her PIN, and certainly the contents of what will be the flow in the reverse direction, which will be the encryption of the web page that shows all of Alice's bank information, right? That information Alice would like to be safe for a long time. So Alice would be pretty upset if an adversary who observed that whole transcript of communication then sat offline for a day and was able to figure out what her password is, what her PIN is, what the contents are of the web page. This actually already suggests some of the subtleties that are involved with defining what privacy is. What if the message going from Alice to Bob, the message is maybe Alice's salary, right? Well, we certainly don't want the adversary to learn all of them, all of the string that encodes Alice's salary. But we're probably even going to be unhappy if the adversary can learn how many digits are in the string that represents her salary, because that already gives the adversary a pretty reasonable amount of information about how much money Alice makes. So there's a lot of subtlety we start to see involved in describing privacy. Is privacy that you can't recover the entire message M? Is it you can't recover 50% of it, 10% of it? Is it that you can't recover the number of bits that are in the message, the parity of those bits? Lots of things like that might, depending on the application, might determine what it means to be private. So what we're going to be after is a notion of privacy that, if achieved, already will achieve all these other, laundry list of things that we want to achieve. So let's talk for a minute now about the authenticity problem. So Alice has some message M. Think of Alice now as maybe being Microsoft trying to send some patch to the operating, some security patch, say, to Bob, who is an owner of the Microsoft operating system. And so, in fact, let's just go ahead and call this message a patch. This is an OS patch. So Alice wants to send an OS patch M down the wire, and she'd really like for Bob to receive this patch because, well, if it's a patch, it's obviously supposed to be doing something useful, like maybe closing a security hole, and so she'd really like for Bob to receive M on the other side, and then install this patch. Of course, Bob's not going to do it; it's going to be the operating system, but Bob installs the patch to, say, close some security hole. Well, that's fine if we have passive adversaries, because in fact, if it's just a patch to the operating system, maybe Alice doesn't even care that the whole world can see what this patch is. Maybe it's actually even good if the whole world sees what the patch is, including adversaries. But what would be disappointing, of course, certainly to Bob, is that if the adversary was not just passive and observing things, but if it was active. So putting on the wire some M prime. Well, if Bob believes that he's actually receiving an OS patch, so I'll put this in quotes because we're not. This is the actual operating system patch, and this is what Bob believes is the operating system patch M prime, and maybe the adversary has in fact taken the patch, interrupted its transmission to Bob, and inserted its own supposed patch on the wire M prime, where this thing in fact now introduces a new security, maybe even a worse security hole. And you can imagine how this might happen. The adversary maybe takes M, and maybe this is like a TCP message going to some particular port, and the adversary stops the transmission of this message, drops it, and maybe just does something simple like flips a few bits in M to make M prime, and then now sends that as a TCP message to the port. Maybe the production of M prime is much more complicated. So in fact, if it's trying to introduce a new security vulnerability into the supposed patch, this might be a much more complicated munging of the original message M. But in any case, this is the idea. The adversary sees M, takes it off the wire, does something to it, and puts back an M prime. And now what Bob receives is this thing M prime, which is probably not the thing that Alice actually sent as an OS patch. So we'd like some way to protect against this, and we're going to stay for the moment in this symmetric setting. So we'll assume that Alice and Bob share secret key K. So they have some secret key K. We haven't said anything yet about how it is they come to share this secret key K, but we'll assume that they do in the symmetric setting. And well, so then perhaps we can hope to do something like in the privacy setting where we used encryption to protect the privacy somehow using the secret key. So here we'll use some other, maybe I'll just call it, I don't know, F for nothing in particular. I just don't want to use A for authenticity because A is also used for adversary. So some processing F that's going to rely on use of the key K, and what should happen over here then is we want for Bob to somehow employ the key in order to determine from this thing, if the adversary were doing nothing, then what would be received on the wire would be F sub K of M. And we'd like for Bob to be able to use his knowledge of the secret key to in fact recover M and determine that the M that it recovers is actually the M that was sent. Yeah, he wants to be able to, maybe it won't be 100% guarantee, but he wants to be very, very sure that whatever he gets out of processing this is in fact the thing that was sent. So let me just sort of give you an example of what one of these might look like. You know, since we said we don't really care necessarily about the privacy, this thing here, it might be something like f sub k of m is m, and then this symbol here means concatenation. This is concatenation, this pipe is concatenation of something that we'll call the tag. And the tag is the thing that actually depends on the secret key k. So in this case, this is what's actually sent on the wire. And if Bob receives it, then he simply looks at m, looks at m, and verifies the tag. Verifies the tag using the secret key k, and if the tag verifies, then he accepts m as the actual message, and if it doesn't, then he doesn't accept m. Yeah, this is the kind of processing that we'll want to use to establish authenticity of what's been sent. Now, of course, if the adversary tries to do something here and changes what's actually on the wire to something else, so let's say that the adversary makes that's bad actually, because that suggests it's a different algorithm. Let's say that this isn't what actually appears on the wire, but if we stay with this model of what's above here, then we can think about maybe what the adversary puts on the wire is like m prime concatenated with the tag, right? This tag. So same tag, he just changes some bits in what m is. And now, when Bob tries, he'll look at m prime, and he'll try to verify that the tag is in fact the right tag for m prime. And if we've done our job properly in creating the tag, then it ought to be the case that the tag won't verify for this m prime. It would only verify for m. Maybe the adversary changes m to m prime and also changes the tag somehow. We still want it to be the case that when Bob tries to verify the tag, he learns that, nope, this tag and this message, they don't go together, so I should reject it. So this is the kind of thing that we'll end up building. It's just one example of what we'll end up building to achieve authenticity of what's sent. Yeah, what's received is actually what was sent. Again, we're in the symmetric setting here because we assume that Alice and Bob share the key. So this this thing we've just described here, this f, this is a symmetric key authenticity providing algorithm. F is the symmetric key authenticity providing algorithm. As an example, yeah. So one thing to notice, one thing that's already suggested by the example that I've given here, make sure this is easily visible on the screen, is that we've just sent m in the clear here, right? So it's obvious that this f that we've just described, which does this processing, this can't be providing privacy in any meaningful way because we've just sent the original message in the clear. So this should already suggest to you that the authenticity problem and the privacy problem are in fact different things. We'll see, maybe in the next lecture or a couple down the road, that it's not the case that encryption alone, which is meant to provide privacy, also provides authenticity. And it's easy to fall into this thinking, right? So before we talked about you have some e sub k here, right? So let me get rid of all this for a second. So we've got some e sub k, and it's intuitive to think that if only Bob and Alice know the key K, then when the adversary, we were calling this the ciphertext C before, if the adversary puts some C prime that's on the wire here, and the adversary doesn't know K, then it's intuitive to think, well, look, if Alice and Bob are the only ones who know K, then if what Bob receives actually decrypts properly to some message, then we ought to believe that it was Alice that sent it, because only Alice shares the key with Bob, and so it only should be Alice that can make ciphertext that will actually decrypt properly. But in fact, that's not the case. Encryption alone is not sufficient to provide authenticity. It's going to provide privacy for us, or need something else to provide authenticity. And in fact, we will see how to make encryption schemes that achieve both of them simultaneously, and these are a kind of cryptographic primitive called authenticated encryption. So that's ultimately where we'll be going with encryption schemes. And in fact, this is most like if you use TLS or SSL or SSH or IPsec, the encryption that's actually being used there is actually implementing one of these authenticated encryption primitives. We'll talk much more about that later. Okay, so this is privacy and authenticity in the symmetric setting. So let me scroll down here a bit and give you what we call these things. So maybe over here, symmetric setting plus privacy. The tool for this is symmetric key encryption. And we'll spend a lot of time in lectures that are coming up soon talking about what an encryption scheme actually is. You already probably have some intuitive idea, but we want to be able to say abstractly, like, what is an encryption scheme? What should it do? What are its operating properties? And essentially describing what an encryption scheme is before we set out to describe what an encryption scheme should do. If you do it the other way around, it's kind of like putting the cart before the horse. You're saying, well, I want something that provides privacy. The question we really should be asking first is, what is this privacy providing thing supposed to look like if I wanted to actually implement it? So symmetric key plus a privacy goal, the tool is symmetric key encryption, symmetric key plus authenticity goal, we'll use a tool called a message authentication code. Otherwise known as a MAC. This is different from the MAC, like the MAC address of something, message authentication code. So we've been talking about this setting in which Alice and Bob are able to potentially achieve privacy and authenticity by virtue of the fact that they share some secret key K that the adversary doesn't have. This is how we created an asymmetry between what Alice and Bob can do and what the adversary can do. But we didn't talk about where this key came from and how it was that Alice and Bob came to share it and the adversary to not have it. This is a whole task in itself to establish this shared key between Alice and Bob. And in fact, there are settings in which this might not be what you want to do at all. In particular, imagine that Alice potentially wants to talk to many Bobs. And well, if you're going to use symmetric key encryption, say for privacy, then Alice is going to need to share a key with each one of those Bobs. And she's not going to want to share the same key across all the Bobs because, what if one of those Bobs suddenly becomes adversarial? Now that adversary has the key and can do, whatever. So we want to come up with a different way to do encryption for settings like this. And so here we're going to talk about what we call the asymmetric setting. Asymmetric key setting. We're going to want to achieve the same goals, privacy and authenticity, but now we want to do it without the benefit of having a shared key. So let's say that Alice wants to send some message to Bob, just as before, and Alice wants this message to be private, so that only Bob. So there's some message M, and we want for Bob to be able to learn message M. So how are we going to do this now that they don't share a key anymore? We're back to this problem of wanting to establish some different computing powers between the parties that are here. So I'm going to reverse the roles. Well, actually, not really. So Alice wants to send this message to Bob. And in the asymmetric setting, we're going to imagine that rather than Alice and Bob sharing a secret, only Bob has the secret key. We'll call this secret key SK for reasons that will be clear in a minute. So, well, okay, only Bob has the secret key, which would seem to cause a problem for Alice. But what Bob is going to do is publish some public piece of information that's associated to the secret key SK. And the point of this public information is to make it so that everyone can do processing that will protect the privacy of message that they want to send to Bob, but only Bob can undo the processing. Yeah, so only Bob has the secret key SK, but everybody has this public knowledge, this public key, PK. So these are terms, I'll put them in quotes, public key and secret key. And you may even have heard in previous classes, maybe you've taken a security class and you've talked about public key encryption. That's what we're setting up here. This is a public key, secret key pair. Bob has the secret piece and everybody, Alice has the public key. In fact, as I say, everybody has the public key, even the adversary, right? And this is exactly what I was saying a moment ago, is that, if Bob wants to be able to receive messages from many Alices, say, then Bob is going to allow this public key to be known by everybody. In fact, the adversary may not always be the adversary. Things are much more fluid in the asymmetric key setting. Maybe the adversary, let's call her Eve. Maybe at some points Bob actually wants to receive information from Eve and wants it to be the case that Alice doesn't learn what that information is, yeah, and vice versa. So we assume everybody has the public key. That's why we call it the public key, but only Bob has the secret key. So we're going to actually achieve this again using encryption. So as before, we have some processing E of M, but now we're going to process using this public key PK. And well, so if we have a passive adversary or no adversary at all, then what's received here is this ciphertext E sub PK, encryption under the public key of M, and then using the secret key, Bob is going to compute the decryption D, and decryption is going to be performed under the secret key. So he computes decryption of what's received, which is this, and this ought to produce M. So here we have again this need to have some kind of invertibility property that having the secret key allows you to undo the encryption under the public key, but we don't want it to be the case that if you try to decrypt under the public key, say, that you get back the message. Yeah, it really ought to only be Bob that can do this decryption properly. Well, so as you can see, Alice can send a message to Bob and Bob can decrypt it. The adversary can send a message to Bob and Bob can decrypt it. So here we again have this authenticity issue, right? The adversary, well, since it's in possession of the public key and it knows the algorithm for encryption just like everybody does, it can compute the, maybe what the adversary puts on the wire is not the ciphertext of M, but of some M prime, yeah, that it made up. Here, the authenticity problem seems even harder because the adversary can actually compute everything, right? It has the public key. And sure enough, if Bob just simply decrypts what comes out and the encryption and decryption are working properly, then Bob really ought to recover M prime, which isn't the thing that Alice sent. So again, we're going to have to be concerned about authenticity of things that are put on the wire. So we'll need another kind of primitive to achieve that. So this is called public key encryption, and the analog of symmetric key authenticity providing algorithm in the asymmetric setting is something that we're going to call a digital signature. And it should provide essentially the same kind of functionality that a Mac does, which is that only Bob ought to be able to create, valid-looking things. Only the holder of the secret key should be able to create valid-looking things. So rather than to go into details of that, if we're in the asymmetric setting, I'll just write it down. If we're in the asymmetric setting and you want privacy, then the tool that we're going to use in this case is just public key. It's called public key encryption. More correctly, I guess, if you're trying to have some sort of parallelism, we would call this asymmetric key encryption. And in fact, sometimes we will, but everybody just calls it public key encryption. Yeah. If you want to do, if you're in the asymmetric setting and you want to achieve authenticity, then what we actually call this thing is a digital signature. Digital signature, which is a much more modern sounding name than a message authentication code, and also in some ways is more evocative of what it is you'd actually be trying to achieve. You want to send something across the wire which effectively acts as your handwritten signature would, so that the receiving party can verify this signature. Yeah, this is Alice's signature, and nobody else could have forged this signature, so what I've received must have come from Alice. That's a digital signature. One thing we can already see if we think about this this drawing we have above, that so in the encryption case, a little bit more. In the case of encryption, we're trying to achieve privacy. Everybody has the public key, and so everybody can make these ciphertexts, and only Bob can undo the encryption by using the secret key. If we're talking about creating some sort of signature, then, well, things actually change here a little bit, right? If we're making signatures, we want it to be the case that Alice sends something to Bob, and erase this for a second. Alice wants to send something to Bob, and Bob needs to be convinced that the thing that Alice has sent is actually the thing that Alice intended to send. Get rid of that. Well, but if everybody has the public key, so let's just call this thing maybe now F, not that color though. So as we did before, we've got this F, and F is going to process M. And well, so what's the problem here if we say that F depends on the public key? And the goal is to make it so that Bob is convinced that what is received is actually from Alice and not from somebody else. Well, if everybody has the public key, then everybody can do what Alice can do. So we can't have the processing that's going to give us authenticity here depend on Bob's public key, because anybody can do that processing. We also can't have it depend on Bob's secret key, because that would require that Alice has Bob's secret key. So instead, what we need is to sort of flip the sense here of whose secret public key pair we're actually using here. So in the asymmetric setting, we'll usually assume that everybody has a public key secret key pair, and it's, the public key portions are published somewhere. So let's say that Alice has a public key secret key pair, PKA for Alice, not to be confused with adversary, and secret key of Alice. So Alice has this. Bob has, of course, his own public key and secret key pair. And we assume that the public key portions are known to everybody. So the adversary has the public key of Alice and the public key of Bob, and Bob has the public key of Alice, and Alice has the public key of Bob. And now we can see how it is. So if Alice wants to send encryption to Bob, then she uses Bob's public key because only Bob knows the secret key that goes with that. If she wants to do some sort of processing that's going to act as a digital signature on this message M, then what she should use, she should be the only one who can make signatures that can make her signature in particular. So the processing here is going to be under the secret key of Alice. Yeah? The adversary doesn't have the secret key of Alice, nor does Bob. But we want it to be the case that anybody, just like if you signed a document and you showed it to anybody who knows you, knowing you in this case means knowing the public key of that person. Anybody who knows you and looks at your signature should be able to say, yes, that's your signature. So we want the same thing to be true here. If Alice signs under her secret key, anybody who knows the public key should be able to verify that this is in fact the valid digital signature. So what happens over here is that Bob verifies using public key of Alice, the digital signature. Yeah, Bob verifies this. Of course, the adversary can verify too, but we don't really care. Everybody should be allowed to verify. What we don't want to be possible is for the adversary to put something else on the wire here that then Bob verifies as being the correct digital signature of Alice. Right? We don't want somebody to be able to forge something to put on the wire here that will convince, we don't want this kind of a thing to be possible. Right? We don't want the adversary to be able to put something on the wire that actually is a correct digital signature under Alice's key of some other message M prime, because in that case, Bob would be able to verify, oh, yeah, this is actually the correct digital signature for M prime, so I should accept M prime. We don't want that to be possible. That's the thing that we'll want to prevent. And this is really nothing more than just saying we want authenticity in the asymmetric setting. So there, in a nutshell, is effectively everything that we're going to be doing in this course. In 10 weeks, it'll take us pretty much all of the 10 weeks, I think, to be able to discuss symmetric key encryption, message authentication codes, public key encryption and digital signatures, and what does it mean to have authenticity? What does it mean to have privacy? How do we build symmetric key encryption schemes that will achieve some formally defined notions of privacy? How do we build MACs that will achieve some formally defined version of authenticity, and so on? This is easily 10 weeks worth of work. These are the core things. As I said, these are the fundamental goals of cryptography. There's certainly, I don't want to give in any way the perspective that these are the only things that cryptography is concerned with. In fact, these are very much the basic things. And even here, it'll take us a whole term to get them right, and also to see ways to get them wrong. But crypto is very much alive and well, and there's lots and lots and lots of interesting problems that fall outside of what's properly given here. And we'll talk about some of these as the course goes on. I'll interject them during lectures when it seems like it's interesting and appropriate. And if there's time at the end, we'll actually talk about other kinds of cryptographic problems. We didn't talk at all about, in the symmetric setting, for example, we just assumed that Alice and Bob came to be in possession of some kind of shared key. That's a separate goal of cryptography. That's key exchange. We want it to be the case that somehow Alice and Bob have a conversation at the end of which they share a secret key K and then can use symmetric key encryption. That's a whole separate problem, key exchange, that we'll maybe have a little time to touch on towards the end. Why would you want to do that? Well, you might want to spend the time to carry out key exchange, because we'll see that symmetric key encryption is orders of magnitude faster than public key encryption. So think like symmetric key encryption, you can do it like, I don't know, 10 cycles per byte of message you want to transmit, and public key encryption is going to take you something like 1,000 cycles per byte that you want to transmit. So you'd really like to transmit as few bits as possible using public key encryption, and then do as many as possible using symmetric key encryption. And so what we'll see is that, in fact, one of the primary uses, in fact, maybe the primary use of public key encryption in the real world, is to establish a shared key. Keys are typically short. Think like 128 bits. So you use public key encryption to help bootstrap the establishment of a short symmetric key, send as few bits as possible using this expensive operation, and then send really all of the actual data that you want to transmit using symmetric key encryption, which is way efficient, under the key that you've established using the public key. In fact, I'm a little bit biased, so I've spent essentially all of my career so far thinking about symmetric key cryptography, symmetric key encryption, authentication codes, authenticated encryption, things like this. So I've worked almost entirely in the symmetric setting. It's the asymmetric setting, the public key setting, that's flashy. Like, this is really where the hard math is. Think about like RSA and discrete log and Diffie-Hellman, if you know any of those kinds of terms. This is where all the fancy math is. But in the real world, this is also where about, like, I don't know, 5–10% of the work is actually done. All of the heavy lifting is done in the symmetric setting. So maybe I'm biased by the work that I've done, but I really prefer to talk about the symmetric setting, and I feel like it doesn't, in some ways, doesn't really get its due in the popular press, because this is sort of like the workhorse of cryptography, and this is the flash of cryptography. In any case, this is essentially what we're going to be thinking about for the next 10 weeks, and yeah, I'm glad you all have joined for this class. It's going to be fun.